Assalamu alaikum. Today we will perform experiment number 12 of the electric circuit analysis lab. Its title is to verify maximum power transfer theorem for different configuration of DC circuits. The objective of this lab are to check the validity of maximum power transfer theorem for DC circuits and to verify the result through software using Proteus. The equipment required for this lab are variable DC power supply, DMM, breadboard, resistors, and connecting wires. Basically, the maximum power transfer theorem is not so much a mean of analysis. In fact, it is an aid to system design. Sometime in engineering, it is required to design a circuit that transfers the maximum power to a load from a given source. The theorem is used to ensure that a load receives maximum power from the source. The statements for this theorem are: a load will receive maximum power from a linear DC network when its total resistive value is exactly equal to the Thevenin resistance for the network as seen by the load. By showing this figure, V Thevenin, R Thevenin and RL. When R Thevenin and RL is exactly equal, then maximum power transfer. Or a load will receive maximum power from a linear DC circuit when its total resistive value is exactly equal to the Norton resistance of the network as seen by the load. When RL and RN is same, then maximum power transfer. If the load resistance is lower or higher than the Thevenin or Norton resistance of the source network, it dissipates. More power will be less than maximum. How to calculate the power for the resistive circuit, and show by calculus this proof the maximum power transfer. In the diagram below, the power is being transferred from the source with voltage V and fixed source resistance Rs to a load with resistance RL. By Ohm law, I is equal to the V by Rs plus RL. By this, I is equal to V by Rs plus RL. The power PL dissipated in the load is the square of the current multiplied by the resistance. PL is equal to I square RL. I equal to V by Rs plus RL square into RL. The final equation is V square by Rs square by RL plus 2Rs plus RL. The value of RL for which this expression is maximum can be calculated by, but it is easier to calculate the value of RL for which the denominator. The denominator Rs square by RL plus 2Rs plus RL is a minimum. The result will be the same in either case differentiating with respect to RL. D by DRL into Rs square by RL plus 2Rs plus RL. By differentiating, the final result is minus Rs square by RL square plus 1. For a maximum or minimum, the first derivative is equal to 0. When this is equal to 0, the Rs square by RL square is equal to 1, or RL is equal to plus minus Rs. In practical resistive circuit, Rs and RL are both positive. To find out whether this solution is a maximum or a minimum, we must differentiate again. By differentiating this, the final result is 2Rs square by RL cube. This is positive for positive value of Rs and RL, showing that the denominator is a minimum and the power is therefore a maximum when Rs is equal to RL. Then maximum power to the load, PL max. In general, for maximum power to the load, RL is equal to R Thevenin. For the above figure, IL is equal to E Thevenin means V Thevenin by RL plus R Thevenin. When RL is equal to R Thevenin, then E Thevenin by 2 R Thevenin. The power is equal to IL square R by putting IL E Thevenin by 2 R Thevenin whole square into R Thevenin. The final equation of PL max is equal to E Thevenin square by 4 R Thevenin. Then maximizing power transfer versus power efficiency. The condition of maximum power transfer does not result in maximum efficiency if efficiency is defined as the ratio of power dissipated by the load to power developed by the source. Then it is straightforward to calculate from the circuit diagram, that is this Vs is into Vs series with Rs and Rl. Efficiency is equal to R load divided by R load plus R source. By simplifying this equation, R load divided by denominator equal 1 by 1 plus R source divided by R load. Consider three practical cases. When R load is equal to R source, then efficiency is equal to 0.5. If R load is infinity, then putting R load is infinity, R source by R load, anything divided by infinity is equal to 0. 1 by 1, efficiency is 1. If R load is equal to 0, anything divided by 0 is infinity. 1 by infinity is equal to 0. Then eta is equal to 0. The efficiency is only 50% when maximum power transfer is achieved. Because we know R load is equal to R source, then maximum power transfer and efficiency is 0.5 means 50%. But approaches 100% as the load resistance approaches infinity, or the source resistance approaches 0. So the total power level tends towards 0 when the load resistance is 0. All the power is consumed inside the source. The power dissipated in a short circuit is 0, so the efficiency is 0. This graph shows the relationship between RL by RS with efficiency and PL by PL max. PL or PL max. When RL by RS is equal to 1, the efficiency is 0.5 and maximum power is transfer showing the by red line and efficiency showing by the blue line. Example. Taking an example of the Thevenin circuit which we study in lab 10, shown below. This V Thevenin is 32 volt, R Thevenin 8 ohm and RL. The maximum power transfer tells us that the load resistance resulting in the greatest power dissipation is equal to the value of the Thevenin resistance. When R Thevenin is RL, then maximum transfer power. With the value of load resistance, the dissipated power will be 32 watt. For example, R Thevenin is 8, RL is 8 and V Thevenin is 32. Then VL across RL, VL is across RL which is 16 volt and also R Thevenin is 16 volt. And current is V Thevenin divided by R Thevenin plus RL which is 2 ampere. Then the power is by V into I square R or V square by R, which is equal to 32 watt, and also RL is 32 watt. The total power is 64. If a lower value of the load resistance, for example RL is 5 ohm instead of 8, for example, so then the power dissipated by the load resistance will decrease. By showing this table, when RL is 5, the power dissipated is 30.26. Power dissipated increase for the both in Thevenin resistance and the total circuit, but it decrease for the load resistor. When RL is 11, then the PL is 31.2 watt and power dissipated across R Thevenin is 22.68, and the total power is decreased, which is 53.89. Then procedure. First we construct the Thevenin circuit of the previous lab as shown below. Thevenin is minus 8.63 volt, Thevenin 2.8 kilo ohm, and RL is which is 6.8 kilo ohm. So in this lab we not fix the value of RL. First we construct the circuit on Proteus and then on hardware. Creating new project. Lab 12. Next. Resistor and battery. First place the battery this direction, then R Thevenin and R L. So we take 7 resistors of different values with one of the value equal to R Thevenin. First we calculate the resistance in hardware using DMM and record the value in data table 12-1. 7 resistors are 1 kilo ohm, 1.5, 2.2, 2.8, 3.3, 4.7 and 6.8 kilo ohm. And then construct the circuit as shown above, taking one of the above mentioned resistor as RL. After verifying that the circuit is properly patched on the breadboard, switch on the power. Measure the value of VL and IL using DMM and record all the values in table 12-2. And then repeat the step number 5 by all value of resistor. Table 12-2. First is theoretical values VL, IL and TL, and then by software and then by hardware. For theoretical values, simply voltage divider and use VL is R1 divided by R Thevenin plus RL into V Thevenin. The theoretical values are calculated by voltage divider, and IL is simply as V Thevenin divided by R Thevenin plus RL, and PL is simply multiplication of VL into IL. One K. Then place DC ammeter. Milliamps. Minus 2.27, and current is also minus 2.27 milliampere. The next value RL is 1.5 kilo. VL is minus 3.01 and current is minus 2.01. Next value of RL is 2.2 kilo. Voltage is minus 3.8 and current is minus 1.73. The next value of RL is 2.8 kilo ohm, which is equal to R Thevenin. VL is minus 4.31 and current is minus 1.54 milliamp. The next value of RL is 3.3 kilo. Voltage is minus 4.67 and current is minus 1.41 milliamp. The next value of RSL is 4.7 and the last value is 6.8 kilo. The last is 6.8. Voltage is minus 6.11 volt and current is minus 0.9 milliamp. After finding the value of VL and IL, we calculate VL, which is equal to VL into IL. By seeing this table, the maximum power transfer at when RL is equal to R Thevenin, which is 2.8 kilo, the value is 6.65 milliwatt. The last step is to make a graph paper and plot the VL versus RL and observe the behavior of this curve and comments on it in a few lines. इससे आपने जो आपका जो VL, PL एंड RL का आपस में ग्राफ बनाना है. इसमें x एक्सिस पे आपके पास RL है और y एक्सिस पे पावर होगी. तो उस कर्व को देख के आपने इसका बिहेवियर बताना है कि क्या है. देन हम इसको हार्डवेयर पे परफॉर्म करेंगे और जो हमारे सॉफ्टवेयर और थ्योरेटिकल के रिजल्ट्स हैं उसके साथ कंपैरिजन करेंगे कि कितने डिफरेंट है. अब जो हमने सर्किट सॉफ्टवेयर पे किया तो उसको हार्डवेयर पे इम्प्लीमेंट करेंगे. तो ये सर्किट है, इसमें हमारे पास आर थेवेनिन 2.8 के और आर एल के हमने कहा था कि हम 7 डिफरेंट वैल्यूज लेंगे. तो ये टेबल हमने थ्योरेटिकल और सॉफ्टवेयर के रिजल्ट्स फिल कर लिए थे. अभी हम इसको हार्डवेयर पे फिल करेंगे. तो सबसे फर्स्ट हमें रजिस्टर चाहिए आर थेवेनिन जो 2.8 के और V हमने -8.63 वोल्ट सेट कर लिया। तो सबसे पहले हम वोल्टेज देख लेते हैं कि हमारे पास ये 8.63 हमने वोल्टेज सेट कर ली। मेरे पास पॉजिटिव आ गया। ये नेगेटिव और ये पॉजिटिव। फर्स्ट हमें चाहिए 2.8 के 1.8 और 1K को आपस में सीरीज में अटैच कर देते। तो ये हमारे पास R7 आ गई, इसको हम मेजर भी कर लेते हैं। तो ये ऑलमोस्ट 2.759 किलो। अब हमें जो फर्स्ट R1 चाहिए वो है 1 किलो। इसको मेजर करते हैं। तो ये 0.981 किलो। ये मेरे पास सर्किट कंप्लीट हो गया। इसको हम सप्लाई कनेक्ट कर देते हैं। पॉजिटिव फर्स्ट में VL मेजर करना। ये -2.269 वोल्ट। देन हम करंट कर लेते हैं। -2.29 पे। नेक्स्ट जो हमारे पास 1.5 किलो। बस देख लेते हैं कि इसकी वैल्यू क्या है। 1.473। ये हमने वोल्टेज मेजर किया तो -3.01। देन करंट मेजर कर लेते हैं। minus 2.02 million. थर्ड हमारे पास रेजिस्टर की वैल्यू क्या थी 2.2 के 2.157 किलो सर्किट में कनेक्ट करते हैं वोल्टेज मेजर करते हैं 1.5 तो ये हमारे पास आ रहे हैं माइनस 3 पॉइंट्स करंट मेजर करने के लिए इसको सर्किट ब्रेक किया और सीरीज में को कनेक्ट करेंगे माइनस 1.74 मिलियन पे तो फर्स्ट थ्री वैल्यूज हमने मेयर कर ली हैं अब हम जो हमारे पास थर्ड तक थेवेनिन और आरएल इसमें सेम थे तो 2.8 का एग्जैक्ट नहीं है हमारे पास तो हम 1.8 और 1K को सीरीज में कनेक्ट कर लेंगे तो इसके वोल्टेज मेजर कर लेते हैं माइनस 4.32 करंट के लिए माइनस 1.54 मिलियन पे और इसके हम रेजिस्टेंस भी देख लेते हैं टू 2.778 थर्ड फोर्थ वैल्यू क्या थी हमारे पास सॉरी फिफ्थ 3.3 ग्रेड सबसे पहले इसकी रेजिस्टेंस मेजर कर लेते हैं 3.25 किलो इसको सर्किट में सीरीज में कनेक्ट किया वोल्टेज क्या आ रहे हैं इसके क्रॉस माइनस 4.67 और मेजर करते हैं माइनस 1.42 मिलियन पे अब हमारे पास दो रजिस्टर हो रहे हैं R6 एंड R7, 4.7 और 6.8. Almost 4.66 kilo. Minus 5.42. इसके बाद करंट मेजर करेंगे इसका. Minus 1.15. Last resistor है 6.8K. Exact 6.80 kilo. सर्किट में इसके क्रॉस वोल्टेज मेजर करेंगे. तो ये -6.13 वोल्ट. इसके बाद इसका करंट मेजर कर लेते हैं. तो ये -0.88 और 89 मिलियन पे. अभी हमने ये सारी वैल्यूज मेजर कर ली. और इसके बाद पावर सिंपली हम कैसे फाइंड करेंगे, VL इंटू IL करके हम PL फाइंड कर लेंगे. अच्छा, फिर भी अगर इस लैब में किसी को कोई भी क्वेरी हो तो आप लोग ईमेल के थ्रू कांटेक्ट कर सकते हैं.